Somewhere beneath the Tsugaru Strait, 40 meters below the seafloor and more than 200 meters below the surface of the water above, a train moves through total darkness at 100 kilometers per hour. Outside the tunnel walls, the Pacific Ocean presses down with a weight that would crush an unprotected diver in seconds. The rock surrounding the tunnel is not solid granite. It is fractured, ancient, saturated with seawater that has been migrating through hairline cracks for millions of years. And yet the tunnel is dry. Not approximately dry. Not damp in an acceptable way. Dry enough that maintenance workers walk its length in ordinary work clothes, dry enough that the electrical systems lining its walls have operated continuously for decades. The ocean is right there, held back by something, and most people who ride through have no idea what that something actually is. Here is the question worth sitting with. The Seikan Tunnel connects the Japanese islands of Honshu and Hokkaido. It is 53.8 kilometers long, making it one of the longest railway tunnels on Earth, and the longest portion of any such tunnel that runs beneath open sea. It was bored through rock that geologists, when they first surveyed it, described as among the most difficult submarine geology ever encountered for a civil engineering project. The intuitive answer to how it stays dry is a simple waterproof membrane, the same logic as a raincoat, some impermeable layer between the tunnel and the water. That answer is wrong. Not partially wrong. Fundamentally wrong. The actual system is almost the reverse of that instinct, and understanding it changes the way you see every deep tunnel ever built. Begin with the geology, because the geology is where this problem starts. The Tsugaru Strait sits atop a zone of intense tectonic activity. The rock beneath it is not a uniform block through which you might cut a clean hole. It is a layered, fractured mass of mudstone, tuffite, and volcanic material, shot through with faults and fissures at unpredictable intervals. When the Japanese National Railways began serious ground investigation in the 1940s and continued it through the 1950s and into the decades before construction began in 1964, their surveyors used a method called exploratory boring, drilling down from the seafloor above to extract core samples at dozens of locations. What those cores revealed was that the rock was not just cracked. It was permeable, meaning water moved through it under pressure, the way water moves through a saturated sponge when you squeeze it. The ocean above was not simply sitting on top of this rock. It was inside it, held in tension in every microscopic void, ready to flow toward any lower pressure space that an excavation might open. This is the physics at the heart of the problem. When you dig a tunnel through saturated rock, you create a zone of lower pressure. Water under pressure always moves toward lower pressure. The tunnel, simply by existing, becomes a drain. Every meter of progress through that rock is an invitation for water to follow. During the construction of the Seikan Tunnel, that invitation was accepted violently on at least two major occasions. In 1971 and again in 1976, catastrophic inflows of seawater flooded sections of the workings. The 1976 inflow was severe enough to halt construction for months. Engineers weren't dealing with a slow seep. They were dealing with the ocean announcing itself through the rock at high velocity. The response to those floods is where the real engineering begins, and it starts not with waterproofing but with grouting. Before any major excavation advance, workers drilled a fan of holes ahead of the tunnel face, sometimes 50 or 60 holes radiating outward like the spines of an umbrella, reaching 10 to 15 meters into the rock that had not yet been touched. Into those holes they injected cement grout under high pressure, forcing the slurry into every crack, every fissure, every void that the water was currently using as a highway. When the grout set, those pathways closed. They also drove grouted rock bolts into the tunnel walls and crown, steel rods anchored in resin and cement that simultaneously reinforced the fractured rock mechanically and sealed the fissures through which water traveled. The grouting was not applied once. It was applied continuously, as a permanent procedure in every section that showed elevated seepage, and in some sections it has continued as an ongoing maintenance operation for decades since the tunnel opened in 1988. Think of this as not building a wall against the water, but slowly stitching the rock itself closed, filling in the gaps in a material that was never watertight to begin with, working from the inside out through the surrounding geology. The tunnel does not resist the water by being impermeable. It reduces the flow to a manageable level by treating the rock around it as the real barrier, then managing what gets through with a second system entirely. Because water still gets through. Roughly 70 tons of seawater per day infiltrates the Seikan Tunnel through the rock and finds its way onto the tunnel floor. 70 tons. That is not a trace amount. That is the weight of a fully loaded articulated truck, arriving as water, every single day, in an enclosed space 200 meters below sea level. If that water were allowed to accumulate, the tunnel would flood in hours. The system that handles it is not a pump you turn on when things get bad. It is a permanent, continuous, industrial pumping infrastructure that has run every day since the tunnel opened. Drainage channels line the base of the tunnel walls, collecting seepage as it arrives. That water flows by gravity to sumps at the lowest points of the tunnel, which are not at the middle but near the undersea section where the profile dips deepest. From those sumps, electrically driven pumps push the water upward through pipes to drainage stations on the shore. The pumping heads involved are significant. Moving water from more than 200 meters below sea level to the surface requires sustained mechanical work against both gravity and pressure. The system is fully redundant, meaning there are backup pumps that can take over if primary units fail, and the power supply to those pumps is treated with the same criticality as the power supply to the signaling systems that keep trains from colliding. If the pumps stop for any extended period, the tunnel fills. That is not a hypothetical. It is the designed failure mode, and preventing it is why the pumping infrastructure is engineered to the same standard as the tunnel structure itself. Which brings us to the false belief that almost everyone carries into this topic. The assumption is that deep tunnels are sealed objects, self-contained, watertight by construction in the same way a submarine is watertight. The engineering truth is the opposite. Deep subsea tunnels are not sealed. They are managed leaks. The goal is never zero water ingress. Zero is unachievable in fractured submarine geology at these depths. The actual engineering goal is to reduce ingress to a rate that the drainage and pumping system can handle continuously, indefinitely, with redundancy built in for equipment failures. The tunnel is not a submarine. It is a controlled drain running through an ocean floor, with the ocean losing to the drain every single day by a carefully maintained margin. This reframing is the trick you can explain to someone else in 2 sentences. The rock around the tunnel is sealed by grouting to slow the water down. The water that still comes through is pumped out, continuously, every day, forever. Those 2 systems together keep 70 tons of daily ocean intrusion from becoming a catastrophe, by turning what could be an overwhelming flood into a predictable, manageable flow. The same logic appears in other deep tunnels, calibrated to different geologies. The Channel Tunnel between England and France, running beneath the English Channel at a maximum depth of roughly 75 meters below the seabed, encounters the chalk marl formation, which is actually far less permeable than the geology under the Tsugaru Strait. Chalk marl was chosen specifically because it is one of the few naturally low permeability rock types found in that region, and the tunnel alignment was adjusted to stay within it. Even so, the Channel Tunnel operates continuous drainage systems. The geology did part of the work that grouting has to do in the Seikan. Different barrier strategy, same underlying principle, reduce ingress, then manage what remains. The Gotthard base tunnel in Switzerland, running 57 kilometers through the Alps and opened in 2016, encounters pressurized groundwater at depths exceeding 2,000 meters in some sections, where pressures are extreme enough that the rock itself behaves plastically. There, the waterproofing strategy involves a composite inner lining with drainage layers behind it, directing water to collection systems rather than allowing pressure to build against the structure. Again, managed flow, not sealed exclusion. What these projects share is an acceptance of a fundamental physical reality. At depth, in fractured and saturated rock, water wins every static contest. You cannot build a wall strong enough and seamless enough to hold it back forever through passive resistance alone. What you can do is understand where it is, slow it down through the geology itself, and then commit to removing whatever arrives for as long as the tunnel exists. The Seikan Tunnel has been doing exactly that since 1988, quietly, in the dark, beneath an ocean that most passengers never think about. The bigger the machine, the simpler the trick that makes it work. Subscribe to see the hidden engineering behind the giants around you.